Good morning, everyone. My name is Michella, and here I have my partner with me, Jotika. On behalf of our team at Binus, thank you for being here. Today, we'll be presenting about our research, a bias evaluation framework, and AI resume classification using Dieselbird, SHAP explainability, and automated fairness flagging. So, let's dive in. We'll move quickly across these sections from introductions to limitations and future directions. So here's what's actually happening in modern hiring. A single job postings receives up to 750 applicants, but only 4 to 6 people get called for interview. And since manual hiring is devastating and prone to human error, now 82% of companies are using AI in hiring, especially in resume classification for job matching. But the problem is AI is also biased, since it was trained on bias in the first place. In fact, in one study, AI favored resumes with male names and white names as opposed to their counterparts by more than 50%. AI is also able to infer demographic attribute from other interrelated variable, also known as proxy variable. Notably, AI often analyzes linguistic patterns rather than merit qualifications, and there haven't been any standard on AI bias evaluation. This, of course, will be a huge problem if we let AI make the decision. But what if we can change that? Well, in this research, we will propose a multi-layered audit framework to detect systematic and linguistic bias in AI-powered resume classification. Currently, there are two types of systematic bias. First is implicit bias, that is obtained from non-obvious attribute like linguistic patterns and proxy variable. And second is explicit bias, that is the obvious attribute in resume, like demographic data and education. To assess and reduce bias, currently there are three approaches. First is pre-processing, where we fix the data before the model touches it, but it still obtains proxy variable. Second is in-processing, where we tweak the model to improve the fairness and model performance, but optimizing one will reduce the other. And finally, a post-processing method where we utilize explainable AI tools like SHAP and LIME, or modify the model output to a certain level. But bias are already achieved from the previous steps. And previous research focuses on statistical parity and not contextual fairness, which is important in hiring. And this is exactly the problem we're solving. We integrate fairness evaluation across all stages of pipeline. Moving into fairness metrics based on five studies across fairness and AI bias, they use three main metrics. First is cross-occupation selection rate that requires the mean suitability score for all class to be roughly equal, per class accuracy parity which opt for equal performance across all occupations class, and disparate impact ratio, which states the ratio of the minority class has to be more than 80% of its majority. But since the dataset has no demographic attribute, we use occupation class, primarily because there are strong correlations between occupation and demographic data. As with explainability AI and interpretations with LLMs, there are two main considerations. The first is the third-party API, and second is the local hosted LLMs. And we use local since it doesn't introduce overhead costs and it protects our users' privacy. Now, into the methodology, we gathered a dataset from Kaggle containing 2,400 resumes across 24 occupations in native PDF format, and we used Dieselbird as opposed to BERT because it is lighter, but still maintaining robust performance. And we start with a raw dataset and perform series of data pre-processing. Then we also split the data with 70-15-15 ratio and perform hybrid sampling to handle the data imbalance in a train set, such as oversample and undersampling. And lastly, we perform tokenizing with Dieselbird. And this is what happens inside the Dieselbird classifier. So the Dieselbird receives the text, tokenizes it using WordPress algorithm, and turns it into multiple overlapping token chunks of length 512 with 256 stride. Then we will put it into Dieselbird sequence classifier and perform softmax function on 24 classes to get predicted outcomes and probability. And finally, we will get the suitability score that represents the model confidence in its occupation classification. The resulting dataset was used for hyperparameter using Optuna and resulting in the following configuration. To measure the model's performance, we use classification metrics such as accuracy, recall, precisions, and F1 score. And the main metrics we use is F1 score, as we want to minimize for both false positive and false negative rate. And for the fairness metrics, we use cross-occupation selection rate, per class accuracy parity, and disparate impact ratio to measure the model performance in making fair decisions. And we identified three main flags. First is these uncertain decisions, which happens when the suitability score is less than 0.627. Second is potential bias, that happens when the SHAP token's absolute mean is more than 0.005. And lastly, fairness risk, where the disparate impact ratio is less than 0.8, indicating the systematic performance imbalance. And for explainability and fairness flagging, we use SHAP to detect if a token positively or negatively impact the suitability score. From here, we can spot if demographic tokens highly influence the decisions, which are predefined tokens like genders and seniority-related words. Our model receives the following score for a 24-class problem. However, the fairness picture is more nuanced. Occupation level accuracy range from 0.33 from agriculture and BPO all the way to 1 for teacher, meaning the model classifies some occupation much more reliably than others. And this alone signals a fairness concern. And looking at cross-occupation selection rate parity, the standard deviation was 0.18, a medium variability, and the result indicate a failure in parity criterion. The model does not treat all 24 occupation classes equally. The disparate impact ratio tells a clear story. 6 out of 24 occupation classes fell below the legal threshold of 0.8, flagged as at risk. Engineering, finance, sales, and teachers, on the other hand, exhibited the four highest disparate impact ratios, exceeding the ratio of 1.19, meaning they were over-selected. On the per-class accuracy parity plot, false positive rate stayed low and consistent across all classes, but true positive rate varied widely. The model is not making equally reliable decisions for everyone. And this is where it gets particularly interesting. Our SHAP analysis identified 386 proxy variable tokens, bias like gendered words and seniority indicators influencing model prediction. For example, a resume containing the word female and experience was more likely to be classified as consultant, meanwhile the resume containing the word boys was less likely to be classified as designer. And these aren't signals, they're demographic proxies, and without SHAP, they'd be completely invisible to the hiring team. And here's the operational impact of our flagging system. Across the test set, 75.9% of the resumes triggered at least one flag, 44.2% were flagged for uncertain decisions, which means the model confidence was below threshold, and 41% were flagged for potential bias, indicating that proxy tokens were influencing the result. 19.3% were flagged for fairness risk, which sits below the disparate impact ratio hold, but critically, 24.1% with no flags represents the framework highest confidence, lowest risk predictions, and a clear signal that the system is working. And here's a concrete example. This resume was correctly predicted as consultant, but with a suitability score of only 0.5, well below our 0.627 threshold, and it triggered all three flags, and Llama 2 produced the following output for HR. In conclusion, this framework does its job in detecting bias in AI job classification through SHAP, fairness flagging, and llama interpretations, and it is designed to detect bias before hiring decisions are made. Performance-wise, we get about 75% on accuracy, precision, recall, and F1 score, meaning our classification model can accurately allocate job titles, and our evaluation framework successfully capture a bias in the classification system through a high disparate impact ratio with 6 occupations exceeding the threshold. Most of the flag resumes shown a gendered and seniority-related tokens influencing 9 occupations at least 75.9% resume is flagged. To be transparent with our limitations, our dataset is limited and contains no explicit demographic label, so the evaluation is done on occupation level. Moreover, the SHAB is limited to 30 resumes per job, and for the classification model, we have not tested against adversarially manipulated resumes. In this research, flag bias is also not compared against concrete mitigation techniques, and this leads us to our future directions, which are to validate the framework to resumes with explicit demographic bias and multilingual resumes, comparing different mitigation techniques and addressing the framework robustness with adversarial testing. We will further test this framework with HR professionals to validate the effectiveness of the model and integrate it with a real-time resume classification system. Thank you.